think the parts do to you.
Oh, you mean that's
All right. So before we get started today, I wanted to make a quick announcement, a pitch for the IQSS and the Statistics Department mixer. It's going to be held tomorrow at 4:30 on the 7th floor of the Science Center, and anyone and everyone is welcome. And there will be cider and cider donuts and just a chance to talk with some like-minded people. So, there you go. This week we are happy to welcome Michael Bronstein, who among his other accomplishments and appointments is a Radcliffe Fellow at the Harvard Institute for Advanced Study. And he'll be presenting work on geometric deep learning and going beyond Euclidean data. Thanks, Michael.
Thank you. So first of all, thanks for the invitation. It's a great pleasure and I would say an honor to be here. So actually I come, I guess, from a very different background than probably most of the people here. My main field of research is computer vision, geometry, and computer graphics. So you may wonder what it has to do with what I'm going to present. I hope that at least for some of you it will be interesting. So I guess everybody here has heard about deep learning. In the past few years, it has made a big impact or even a breakthrough in several domains, in particular in computer vision and image analysis. It amounted to nearly a revolution, finally making this field working in practice. So you can find many applications of computer vision, for example, in self-driving cars that everybody is talking about. These are just a few examples of articles from the popular press that basically praising deep learning as the next big thing, and that was a few years ago. And basically, it's been around for a while, what is called today deep learning. It's just recently that it has attracted so much attention, especially from the industry, basically becoming already a mature and working technology. So this is, in our field in computer vision, this is the figure that you would usually see when, basically when trying to visualize the impact of deep learning on the field. So this is a famous ImageNet benchmark. Basically, it consists in classifying images based on the objects that they contain, 1,000 different categories. You see an image containing a cat, and you need to say that this is a cat. So the error rate that existed before was close to 30%. Nowadays, it's below 3%. Human error rate is about 4%. So it's already better than human on this particular task. And this is all thanks to deep learning.
How would you know you're doing better than humans?
Well, because basically humans, in some cases, it's very difficult, actually, even for humans, for example, to tell an airplane from a bird. So there is a ground truth. You know what there is in an image, but you give it to, you show it to several representative human observers, and they also make their mistakes. So this is what is considered the human error rate. And basically, the past 5 years, basically the winning methods were all based on deep neural networks. Okay, so the success of deep learning, even though deep neural networks have been around for a while, basically it's a confluence of three major factors. Of course, advances in the architectures and basically the way that these neural networks are structured, but mostly computational power, because the big breakthrough came with programmable graphics hardware, GPUs, which are very efficient for this kind of computations, and mostly the availability of large data sets, because most of the successful applications of deep learning are what is called supervised learning, basically where you give an example and a label that accompanies this example. And basically nowadays we have very large data sets, at least in some applications which can be leveraged for this kind of learning. Actually, there is somewhat a controversial claim saying that data is more important than algorithms, and basically looking at the time it takes from the publication of an algorithm to a breakthrough, several milestones in artificial intelligence, and from the publication of the data set that on which the algorithm was trained. So from the publication of the data set, it's about 3 years. From the publication of the algorithm, it's about 18 years on average.
3 years until what?
So basically, ImageNet, for example, was published in 2010. The winning method that was trained on ImageNet was a convolutional neural network that was proposed in '89. So it's a little bit of a stretch because it's not exactly the same algorithm. It had certain modifications, but conceptually it's the same type of neural networks that were proposed in the late '80s. So it's.
I don't quite know what you mean. So sorry, what's 3 years and what's 18 years?
So that's the average. So that's time when the data set was published. That's the time when the algorithm was published. So this algorithm, convolutional neural network, was trained on this data set to make a certain breakthrough. Basically, it was the winning algorithm on the ImageNet benchmark. Right? So basically, the average time, if you look at several milestones, important milestones in artificial intelligence, like winning, for example, the Go player.
They're not really data sets, they're different versions of models, basically.
So these are models, and these are data sets. So basically,
But the ImageNet, well,
The ImageNet corpus.
corpus,
Yeah,
I guess that's
exactly.
right.
Exactly. So basically, it's both data set and benchmark.
Okay, so we just get better when we use it as they're training data sets.
Exactly.
We get a better training data set. Yeah.
Exactly. So in that case, the large size of the ImageNet was the game changer.
Do you have a sense of are the algorithms being used from sort of the 80s because sort of there's only so many kind of roughly good ideas and they were done then? Or are people still coming up with algorithms now that you think are actually sort of fundamentally different, better in kind of an important way?
So, well, basically, if you look at the architecture that was used in the 80s, it was much simpler. So now with existing computational power and existing amount of data, you can make the same neural network just much deeper, many more layers, many more parameters, and basically in order to determine all these parameters, you need a lot more data. Otherwise, you will overfit. So that's why basically all the three things are important. The algorithm, which existed for several years, but it was not very practical before. But now when you have computational power to implement this algorithm, but sufficiently complex, and a large set of data to train it, then suddenly it starts working.
But there are new algorithms that are being successful, that are proving successful in these problems that are still being developed, right? Like
Of course.
adversarial nets.
Of course. So adversarial, well, yeah, I don't know how much we want to dive into it. So of course, adversarial neural networks are now, for certain types of applications, mostly for image synthesis, are basically making a big change. But still, the fundamentals they're mostly used in conjunction with convolutional neural networks. So basically, the basic building blocks are still the same. Okay, so if we look at the successes of deep learning, most of the research has focused, and most of the successes came in fields where data has some kind of underlying Euclidean structure, grid-like structure. For example, an image, basically, it's a matrix of pixels, right? Another application where it was very successful, for example, speech recognition. So again, audio signal, you can think of it as one-dimensional grid, right? So it has some clear, very well-structured space that underlies the signal. But we are mostly interested in, and especially in recent years with the emergence of, let's say, social networks and other large-scale networks of different kinds, in other types of data that do not necessarily have this underlying Euclidean structure. So again, social networks are a good example. Basically, these are very large-scale graphs. And graphs are basically very good models for modeling interactions, affinities, similarities between different kind of things, right? You can think of applications from biology, for example, regulatory networks, functional networks in brain imaging. In my field, in computer graphics, computer vision, it is very common to model three-dimensional objects as meshes. So basically, these are graphs with some additional information. Basically, these are discrete manifolds. And basically, it is not so obvious how to generalize the successful deep learning methods to this kind of data. Okay, so basically, what I would like to show today is several ways to doing deep learning on graphs. Okay, so here we need to distinguish between several applications. So roughly we can distinguish between two different classes of applications. One of them deals with the, basically we need to make a decision on the entire graph. Okay, so as an example of application, consider a molecule. So this is also modeled as a graph. Atoms are vertices and chemical bonds are vertices, are edges, sorry. And you want, for example, to decide whether this molecule is toxic or not, or it's efficient against certain pathogen. So this is actually a type of applications that have emerged in the past approximately 2 years. And they are making a big difference in this field of drug or material design. Okay, so basically somehow we need to aggregate local information into global information. So if we compare this kind of application to problems in computer vision, this is like image recognition. So you start with an image, you need to say something about the entire image, whether, for example, it contains a cat. Okay? Another type of applications where we want to do vertex-wise decisions. For example, we are given a social network and we have some information about the users, let's say age, gender, education, work, whatever, and we want to predict whether a user would vote for Hillary Clinton or Donald Trump in the past elections. Okay, so basically here the decision is vertex-wise, so it's kind of labeling application. And again, if we take analogy to computer vision, this is equivalent to semantic labeling or semantic segmentation, where we want to label each pixel with whether it's a person, background, foreground, and so on and so forth. Okay, another distinction we can make is whether the graph is fixed or it is changing. Okay, so in the social network analysis, for example, it is reasonable to assume that at least a given snapshot of social network is something that doesn't change in time. Okay, if we consider other applications in computer graphics and computer vision, and I mostly will not talk about it, maybe towards the end if I have time, we cannot make this assumption. So we want, for example, if we model shapes as graphs, we want to learn our models on a given set of shapes and then apply them to new previously unseen ones. So basically the underlying domain changes. Not only that it's not Euclidean, but it can also be different. It will make actually a fundamental difference in the methods that we can use. Okay, so I will start with a very brief description of what deep neural networks are and what are the basic ingredients. Then we'll try to generalize them to non-Euclidean settings, to graphs, first using spectral methods. So we'll talk about Fourier analysis on graphs. And then we'll see several extensions, for example, applications where you have multiple graphs, and this has to do with applications like recommender systems or matrix completion. And then I hope I have time at the end to talk also about spatial domain methods and maybe some examples of more exotic applications like in high energy physics or biomedicine. Okay? And of course, feel free to interrupt me anytime. And basically, the main reference I'm using for this talk is this paper that appeared a few months ago in the IEEE Signal Processing magazine. So basically, it's a review paper that, to some extent, is already obsolete because this is a very actively developing field. But at least it summarizes the main problems and the main concepts. Okay. Okay, so what is a neural network? So let's start with a very basic thing. Let's say that we take an image. Okay, so it's a collection of pixels. We can think of it as an n-dimensional vector, right? We just column stack, for example, all the pixels, and that will be an input. We can multiply it by some weights that are denoted here by W, sum them up, and pass it through some nonlinear function that usually looks something like hyperbolic tangent or sigmoid function. Okay, and basically these W's, the weights, are the parameters of the neural network. Okay, so that's the very simple neural network called the perceptron, proposed in the end of the 50s. So basically it's a nonlinear function, parametric nonlinear function, and you can, for example, make a classification to say whether it's digit 3 or something else. Okay, for example, at the output you will produce 0 or 1. Okay, so you can take this idea, you can make it more complex, you can make multi-dimensional output. You can combine these layers together, basically applying the same operation on the output of the previous layer. So actually, it was shown that it's enough to have a neural network with one what is called hidden layer, so basically 2 layers like this, that it can act as a universal approximator. So basically, it can approximate any continuous function. So this is a kind of strong result, but it's weak at the same time because it doesn't say how to do it. Basically, it doesn't say anything about the efficiency, how many layers or how many neurons you will have, and actually how to find these optimal parameters. So, and in particular, such networks tend to overfit a lot. And in case of image analysis, one of the big problems, for example, if I take now my digit 3 and I shift it a little bit, so the weights that I need to find to tell that this is 3 and this is 3 will be totally different. So basically, this naive approach doesn't have any translation invariance, right? So one of the basically why convolutional neural networks were so successful, one of the at least in image analysis, was the observation that actually data is self-similar across the domain. So if I look at the image, for example, I look at a small window here, I will find roughly the same content somewhere else in the image. So if I were to detect, for example, this kind of an edge in an image, I really need to basically to look at a small template and match it to different portions of the image, right? So that's the idea of a convolutional neural network. Basically, instead of applying, doing these linear combinations followed by nonlinear transformation, considering all the pixels, it looks only at a local receptive field, what is called, basically it convolves the image with a set of filters that are learnable. These are the parameters of the network, and produces a set of what is called feature maps. Okay, so basically the previous linear combinations are now replaced by convolution operations. Okay, and usually in image recognition applications, this is also followed by a nonlinear operation that is called pooling. Basically, pooling reduces the dimensionality of the image. So, for example, if this is a result of a convolution, you will take a block of, let's say, 2 by 2 pixels and compute a maximum in this block of pixels, and then you get a smaller image. So there are several explanations why this particular max pooling operation is efficient. It allows to be invariant or approximately invariant to small perturbations of the image. So, for example, if I move the image locally a little bit, the output of the maximum approximately will not change.
What determines the size of the grid that you apply the max operator to?
It's one of the parameters of the architecture. Yeah. So there are many design considerations that do not have necessarily a good explanation. So roughly, if you start with an image of certain size, let's say if you downsample twice in each dimension, then basically the number of layers will be logarithmic in the image size, right? That you need to do. So basically, it has implications on the number of parameters and the cost of the computation. Okay, and basically, because we combine several layers, what emerges in after the neural network is trained on let's say, natural images, we'll find out that the first layers, the convolutional filters that we find, contain very primitive visual structures like directed edges, for example. If you go to deeper layers, you will see some features that contain maybe corners and some primitive shapes. And at very deep layers, you will see already some high-level concepts like cats, dogs, etc. And basically, this compositionality and hierarchical structure is what allows to build gradually complex concepts from primitive elements. So to summarize, basically the key properties of convolutional neural networks are these self-similarity or translation invariance. This actually stems from the translation invariance of the convolution operation itself. Multiple layers, basically, it's a way of implementing this compositionality. The filters are localized in space. So basically, this is a weight sharing. You don't need huge number of parameters. You have small number of parameters for a filter, and then you assume that the same structure can appear elsewhere. So mathematically, the number of parameters per filter is order of 1, independent on the input size. Basically, you have small patches that you run across your image, and the complexity of computation is order of n. So basically, you run a template over an image. You visit each pixel once. That's why it's order of n. N is the number of pixels. That's the input size. Okay. So basically, many of these properties, maybe with the exception of translation invariance, also appear in graphs. So, for example, compositionality or hierarchical structures also are known to be important in graphs. Locality is also important, and basically, we want also to replicate these properties. We want our implementation of neural networks on graphs to be efficient and have small number of parameters. Otherwise, of course, we'll be prone to overfitting. Okay.
What's the property that governs the notion that if I'm at, say, the upper left-hand corner of an image, that the things that are happening there are going to be most related to other pixels that are near it, rather than simply, say, the bottom right.
So that's locality, right?
So
basically, you want your filter to be small, right? Basically, the filter doesn't care about what happens far away, right? But basically, it depends on the scale, because once you add layers on top of layers, you will be capturing also more distant relations. Okay, but the filter itself, usually these are very small filters in images, something like 5 by 5 pixels.
Is self-similarity a data reduction technique? I mean, if you had infinite computing power, would you look around for all the self-similar groups?
So self-similarity, basically, it's a way of reducing, it's a way of sharing weights, right? So the weight that will be applied at this portion of the image and this portion of the image, it will be the same weight. If you were to apply weights to each pixel, let's say if you have an image of 1,000 by 1,000, that's already million weights. And if you stack multiple layers like this, basically, you will run into the curse of dimensionality. It will be impossible even with infinitely large data sets or
So
data
what's-
sets that are available in practice, you will not be able to determine all these parameters.
So what's the self-similarity giving you then?
Computational feasibility.
Exactly. So basically, you have a small template that you can run
Oh, I see.
across the entire image.
So,
So basically, you want to work locally.
so
Both
it's,
for
like you're summarizing without losing information, basically.
Exactly. Or at least it's a good approximation.
Right.
So the question is basically how to do it on graphs. So in images, it's very simple. So we have basically two fundamental operations. We have convolution and we have pooling, right? So these are the things that we want to generalize to graphs. And if you think of convolution, basically you can think of it as template matching, right? You extract a patch of pixels at certain location, you multiply it by some template, right? And template is determined during the training. You sum up the results of this multiplication. That's the result of convolution, or more correctly, correlation. And then you move the window to the next location, right? So basically, this extraction of the patch is exactly the same at each point. That's why it's shift invariant. Okay. Now on a graph, you don't even have it's not clear what's the notion of a page, right? The number of neighbors at a given vertex can be very different, right? So you don't have a grid structure. And let's see actually how to do it, basically. Let's start with generalization of the convolution, okay? So let's introduce some notation. Basically, we'll be considering weighted undirected graphs, right, with n vertices and non-negative weights. And we are interested in functions that live on the vertices. Okay, you can think of them as n-dimensional vectors. So that will be our representation. So we can color each vertex, and that will be some information that lives on the graph. Okay, and we can define inner product in this space of functions. So you can write it just simply as inner product of vectors. And basically this gives us a Hilbert space, right? We can add or subtract or multiply by scalars functions that live on vertices of the graph. And a fundamental operator that we'll be using is the Laplacian operator. So Laplacian operator, in this case an unnormalized Laplacian operator, it's a way of basically looking at the local average on the of the function around the vertex and subtracting it from the value of the vertex itself. Okay, so that's the way it is written. W, I remind you, are the edge weights on the graph, and if you rewrite this sum slightly differently, this is what you get. Okay, so if you divide everything by this sum of the weights, what is usually called the degree in graph theory, you will get here the average in the neighborhood of vertex I, right? Basically the vertices that are directly connected, and that will be the value of the function at the vertex itself. Okay, so it's this kind of local averaging and difference. Yeah. Question?
I'm sorry, you're saying that your functions are represented, F is a vector of weights,
So
one
F,
weight per vertex?
Yeah, exactly. So it's some numbers on vertices. So I assume real functions on vertices.
But, so you have some F, but you're not actually thinking of F as the function, you're thinking of you're thinking of the result of the function applied to every vertex. So F is in Rn?
So F itself, well, it's a function that lives on a discrete space. So basically on each vertex you have a value. Right, so it's an n-dimensional vector.
Wait, for each vertex it has a value.
Yeah, exactly.
But if it's only defined for your n vertices, how is that different than just calling it a vector in Rn?
That's exactly what we do. That's a vector in Rn, right?
So why are you calling that a function?
Well, it's a function on a discrete space, but it can be represented as an n-dimensional vector, right? So if instead of a graph you had, for example, a real line, it will be a function on a real line. Here, your space is discrete. It has n points.
I guess my question is, if you come up with a different graph, is F going to be still defined, or is F specific to the one graph you're looking at, or is?
Well, in
that
this case, the
something-
n will be the dimension of the graph, right?
Yeah.
So if basically you are saying if you want to transfer a function from one graph to another graph, you need to know basically how to put in correspondence the vertices of the graph.
And you're just not specifying that. So right now we can just think of F as.
I'm considering the graph is given, so that's my domain. Yeah.
So why? I guess I just don't understand why you're calling it a function. Why not just call it the value of the vertices at all of?
Well, it is a function that is defined on a graph, but you can think of it as a vector, right? So if it's a vector, and then the Laplacian will be an n by n matrix that is applied to this vector. So you give a vector, you output a vector, right? So this is how the Laplacian looks like. It's the degree matrix, diagonal matrix containing the sums of the weights minus the matrix of the weights, assuming that if there is no edge, then the weight is 0, right? And when you apply the matrix delta to your vector, you get exactly this operation. Yeah.
Could you give an example of an F?
Sorry?
Could you give an example of an F?
Example of an F? Well, for example, here, think of colors. Let's say blue colors are negative, hot colors are positive numbers, right? So something like this. Let's say you have, think of for example, weather stations positioned at some points, right? And for example, the temperature that they measure at a certain point of time. And the connections between them, for example, will be proximity. So something like this.
Then the Laplacian in the next slide is just, it's just relative then to the sort of local set of other nodes that weather station is connected to.
Exactly.
So how close am I to you relative to my connections with other people in this room?
So in this case, probably the W's will be somehow representative of the distance between weather stations, right? Okay, so that's basically, you can write it as a matrix form, right? And again, from now on, basically you can think of these functions and vertices of the graph as n-dimensional vectors, right? So we can do it as matrix vector operations. And basically the geometric interpretation of the Laplacian, or the physical interpretation of the Laplacian, you can think of it as basically how smooth the function is, right? So basically because it averages the function in the proximity of a vertex and subtracts it from the vertex itself, basically if the function is varying slowly on a graph, this difference will be close to 0, right? So if I show you this signal and this signal, which one is smoother? Obviously this one, right? Here the function changes slower. Here it changes, basically it jumps across adjacent vertices, right? So a way to measure it will be looking at the differences between Fi and Fj, where I and j will be adjacent vertices. Take the square weighted by Wij, right? And this is nothing else but this quadratic form F transpose delta F, right? In physics, this is called the Dirichlet energy. Basically, it measures a notion of smoothness, or how fast the function changes.
Is there a reason why you're comparing it to the average rather than some other operator? I mean, before you were using the max operator as the sort of relevant last.
So excellent question. You can do it differently, but it will be a non-linear operation. So here the advantage, there are non-linear versions of Laplacians, or Laplacian type operators. It's convenient to work with linear operations because you can write it as a matrix. We'll see in a second that basically we'll be also deriving an orthogonal basis that is related to the Laplacian. You can also define some kind of eigenfunctions of nonlinear operations, but it's more complicated. There are, for example, L infinity or L1 Laplacians. So you just replace, for example, this square with absolute value, right? And you can say that that's my energy. I want to find its eigenmodes. So people do it. It's just more complicated.
I'm sorry. Your second bullet, what is represented as a positive semi-definite?
The Laplacian operator.
Which is only indexed by I.
So the Laplacian operator, that's the output of Laplacian at vertex I.
Right, so how do you end up with an n by n matrix if you only have something that's indexed by I?
So this is for I going from 1 to n.
Okay.
Okay, so that's the Laplacian at the vertex I. Basically, to compute the Laplacian, you take average in your, over all your neighbors and subtract this average from the value of the vertex itself. Okay, and you do the same thing for all your vertices.
Wouldn't that give you n numbers?
Exactly, but multiplication of a matrix by a vector gives you n numbers.
Oh, I understand.
Okay.
Thank you.
Okay, so next, why this is important? Basically, you can ask the following question. Basically, now we have a measure of smoothness on a graph, right? That basically the Laplacian allows to tell us whether the function is smooth or not, right? It varies fast or slowly. So basically, you can ask the following question. Let's build an orthogonal basis. Orthogonal meaning that all the functions are basically are orthogonal to each other in the sense of the inner product that we defined, right? That inner product of phi k and phi other with other index not equal to k will be 0, right? And also they will have unit length, so unit norm, and we want minimum Dirichlet energy. We want basically the smoothest basis possible. Okay, so a different way of writing it algebraically is to minimize the trace, basically the sum of the diagonal elements of this matrix, under the constraint that phi transpose phi equals to I. Basically, this is orthogonality. Okay, and this is a very well-known problem in algebra, and the solution is basically these phi will be the Laplacian eigenvectors. Okay. Now, and this is how you write the Laplacian eigenvectors, right? So the Laplacian in this case for undirected graph, it's a symmetric matrix. So it has this decomposition. Basically, you can write it as a product of an orthogonal matrix and its transpose, and in the middle it's a diagonal matrix containing the corresponding eigenvalues, okay? Which also happen to be non-negative, so it's positive semi-definite matrix. And why is it important? Because if we consider the standard one-dimensional Euclidean Laplacian, which is just second-order derivative, its eigenfunction form what we know as the Fourier basis, sines or cosines, right? So basically the smoothest signal possible, the smoothest signal is a constant, right? Basically, it doesn't change at all, right? So the second function that is orthogonal to the constant, but changes the least will be a full period of sine or cosine, right? Because it's basically it has the same amount of negative values as positive values. Basically, it's integral, right? The inner product with 1 will be 0, right? So they will be orthogonal, and so on and so forth. You continue like this, you get integer periods of sines and cosines. Okay, so this is what we know as Fourier basis. So Fourier basis is the smoothest orthogonal basis, right? And this is how it will look on the graph. So we can also compute eigenvectors of a graph Laplacian. You will get something like this. The first one will be a constant vector, and then basically its kind of frequency will be increasing, right? So basically the changes between negative and positive values will happen more frequently. So actually the corresponding eigenvalue, you can think of it as a kind of frequency in the usual frequency analysis.
So this decomposition, so you're taking your graph structure as fixed, but in this, so all of your edge weights and everything, they're all fixed.
It's all encoded in the Laplacian, yeah.
Right, but you're not your outcomes, or the value of, this is independent of f, this is coming up with f, collection of f's that are
No,
smooth,
it's independent of f, it's only a function of the graph. So basically, I give you a graph, you can produce such a basis.
So
okay?
Without, for example, your coloring of your nodes or anything, this is a statement about the structure of the graph,
Exactly.
not the outcome.
Exactly, about the connectivity of the graph and the weights, right? So the second step, of course, we want to, given some function on the graph, we want to represent it in these bases. So that will be the Fourier analysis, right? So what is Fourier analysis in the classical sense? I remind you, you can take a function, let's say, on an interval between minus pi and plus pi, and represent it as these Fourier series, right? So basically, this will be a projection of a function on some basis, right? In this case, these are complex exponentials or sines and cosines, right? So this will be the Fourier transform or Fourier coefficient, right? And basically summing them up with the same basis functions gives us, reconstructs the signal back, okay? So you can think of it as this is the Fourier transform and that's the inverse Fourier transform, or analysis and synthesis in signal processing terms. Okay, and here the Fourier basis, again, it's the set of Laplacian eigenfunctions, right? These are eigenfunctions of the second order derivative operator in the Euclidean setting. So we can use exactly the same construction on a general graph by replacing these exponentials or sines and cosines with the eigenfunctions of the graph Laplacian. Okay, so that's exactly the same thing. We take the inner product of our function with the basis functions, right? So this gives me the Fourier transform, and I multiply these coefficients by the basis function and sum them up. This reconstructs me back the original function. Okay. And again, here the basis functions are the orthogonal eigenfunctions of the Laplacian. Now, what does it have to do with the convolution? I remind you, this is how convolution looks in the classical setting. It's given by this integral, and the main property of convolution is shift invariance. So if I convolve f with g and I move f by some x0, then it is equal to the result of the convolution shifted by the same amount. Okay, and this is known as the convolution theorem. Basically, the Fourier transform diagonalizes this convolution operator, and basically it means that convolution in the Fourier domain can be computed as point-wise product of the Fourier transforms. Okay, so this is bread and butter of signal processing because in the Euclidean case we can compute Fourier transform efficiently using fast Fourier transform algorithms in n log n complexity. Okay, and usually usually this is your signal, this is your filter, and usually the filter is already represented in the frequency domain. So basically you take your signal, you compute its Fourier transform in a fast way, then you filter it, and then you compute the inverse Fourier transform, right? So this is how all signal processing more or less is working, okay? Now, this is how the convolution looks like in the discrete case, still Euclidean case, right? So you can write the convolution as basically as a matrix, as a linear operator that looks like this. So these are the elements of the filter G in the spatial domain that are put into this matrix. That you can see it has this what is called circle and structure. So basically each subsequent row is the previous row that is shifted by one position, okay, and wrapped around. Okay, so this is called toplets or circulant matrix, and these matrices are known to be diagonalized in the Fourier basis. So basically if I represent it in the Fourier basis, that's exactly how it looks like, a diagonal matrix, and the diagonal will be the values of the Fourier transform of G, okay, the classical Fourier transform. And this is the Fourier transform of F, right? It's F multiplied by the vectors phi, right, contained as columns of this matrix phi. So this is the Fourier transform of F. Product with diagonal matrix is element-wise product, right? And we get the convolution theorem. Okay, so this is product of Fourier transforms of F and G, and that's the inverse Fourier transform. Okay, so that's the convolution of F and G. Okay, is it clear? Okay, so basically this is a property in the Euclidean case. In the non-Euclidean case, we don't have shift invariance. Basically, we cannot even define it properly on a graph. So we can use what is a property in the Euclidean case as a new definition of convolution in the non-Euclidean case. So basically, we can say that we define spectral convolution as a product of the Fourier transforms of our signals. So that's Fourier transform of F, that's Fourier transform of G, and that's their product in the frequency domain, right? And that's the inverse Fourier transform. So we can define convolution in this way. It is not shift invariant anymore, right? So this is how we write it in the matrix vector notation, right? So that's Fourier transform of F, that's Fourier transform of G, this is element-wise product, that's inverse Fourier transform. Or we can simply write, basically, if we represent if we call the Fourier transform of G as G hat, basically this will be a diagonal matrix containing the Fourier coefficients, okay? So it's not shift invariant. This matrix G doesn't have any circle and structure anymore. What is also implicitly hidden here is that basically this basis is assumed to be fixed, right? We assume that the graph is given. If the graph changes, the basis will also change, right? The Laplacian will change and its eigenfunctions will change. So basically, if the consequence will be, I hope we'll get to it at the very end, I doubt it actually. Basically, if we change the graph, then the basis changes, and if we learn the filter with respect to one basis, we cannot apply the same filter on a different graph. Okay. So basically, this is a way of generalizing convolutional neural networks. Basically, you can define the convolution in this way, as we've seen before. In this case, W is an n by n diagonal matrix. These are the spectral filter coefficients, and we learn them during optimization. And all the rest is the same. So that's the convolution operation in the convolutional layer of convolutional neural network. So that was one of the first ideas of generalizing convolutional neural networks to graph. Besides being the first work, everything is bad here. So, well, filters are basis dependent. So that's inherent problem of spectral approaches in general. We have n parameters per layer. The matrix is diagonal, so it has n diagonal elements, right? While we wanted order of 1 parameters per layer, independent on the input size. The cost of computation, basically computing these Fourier transforms, phi transpose and phi, on graphs we don't have FFT algorithms. So usually it is order of n squared. It's multiplication by a dense n by n matrix. So it doesn't have a special structure that allows to do it with logarithmic complexity. And also the filters are not localized. So basically we are computing some filter. God knows how it will look like in the spatial domain, right? So we don't have this important property of that we had in the classical convolutional neural networks.
And this was all over an undirected graph.
This is undirected graph.
So it hits the fan even worse with a directed graph.
So with the directed graph, there is a problem that the Laplacian matrix is not symmetric, so you don't have an orthogonal eigendecomposition. There are ways of dealing with directed graphs, but I didn't plan to show it because of lack of time. But if you're interested, I can talk about
The
directed
intuition
graphs.
of it gets worse is correct.
Yeah, it gets worse. That's, if you summarize it in one word, that's correct. Okay, so let's start from the last point. Basically, what do we do with spatial localization? Okay, so in the classical sense, in the classical case again, there is this property that relates the integral of higher order derivatives of the Fourier transform with the higher order moments of the function, of the original function in the spatial domain, right? So basically, if I want my function to be localized, I want the higher order moments to ideally vanish, or at least to be very small, right? For increasing k, right? It means that basically, if you think of it as a distribution, it will have tails that go sufficiently fast to 0, right? So it means that basically the equivalent of it it tells us that the higher order derivatives of the Fourier transform must also vanish, right? Because of this relation. So it means that spatial localization translates into smoothness in the frequency domain, right? The Fourier transform must be smooth. Vanishing higher order derivatives are equivalent to smoothness, okay? Now, smoothness here is understood with respect to the frequency, which in our case is understood as the eigenvalue of the Laplacian. Okay? So basically, we want, in this case, to parameterize the spectral filter as a transfer function, basically as a function of parameter lambda, the frequency, and this function must be smooth. Okay, and we apply this function to the Laplacian, which is equivalent to applying it to the eigenvalues of the Laplacian, right? So basically, I can write the non-linear function of a Laplacian, and it is understood in this sense that I apply this function to the eigenvalues of the Laplacian in this way, right? It's diagonal magic, so I apply it to each of the eigenvalues. And this function is parametric. Basically, it's parameterized by a small number of parameters, ideally order of 1 with respect to the input size, okay? Independent on the size of the matrix. And one class of such filters are polynomials. Or it's better to work with Chebyshev polynomials, which are orthogonal, but for simplicity, let's say polynomials. Okay? So polynomial of order R, it has R coefficients, or R plus 1 coefficients, and it is a smooth function, right? So basically, this is a class of filters that we can apply to our Laplacian. So the number of parameters here is fixed. The filters have guaranteed compact support. And why is that? Because basically, when we apply to the Laplacian is a local operator. To compute the Laplacian, you touch only your neighbors, right, of a vertex. So for example, the second power of the Laplacian, you touch the neighbors of the neighbors, right? The rth power of the Laplacian, you touch r times the neighbors of the neighbors. So basically, the result is localized in space. Okay? It has r-hops support on the graph. You don't have any explicit computation, explicit eigendecomposition of the Laplacian, right? You just apply the Laplacian or its powers to your function r times. Okay, so the computational complexity is order of n. Okay, so let's see some examples of application. So this is a citation network. Here, the vertices of the graph are papers. The edges are citation, whether a paper cites each other or not. And in this case, the graph is assumed to be undirected, which actually loses important information. And we have some information about the content of the paper in the form of some feature vector at each of the vertices. The goal here is to classify the field in which the paper was published. Okay, so this is, in particular in this case, it's the core dataset. It's rather small and simple dataset, but still it is used by different algorithms. So here are different results of this classification problem. So all these methods are not using any neighborhood information. They are using just the feature vectors at each vertex. So they treat vertex separately without considering the neighborhood. And this is the spectral graph CNN. So you can see that it produces significantly better results because probably the context is important. And basically, these methods, for example, they're very recent. So it's not that we are comparing to very old methods. This is from 2016, something like this. Yeah.
Say a few words about the training and test set.
Sure. So this is okay. So excellent question. So this is what is called a semi-supervised setting. So here we assume that the labels in some of the vertices are given, so they are used as a training set, and we try to predict the other vertices that were left out. So it's a kind of diffusion or interpolation of labels.
So just to recap, the parameters that you're learning are the alphas.
The parameters,
And
exactly.
the
These are the
WIGs in the
the coefficients of the polynomial. Yeah.
and the WIGs that
Well, so in this case, you don't have WIJ, you have alphas,
just those.
and you have
the
you might
WIGs
have
come
several.
from your problem in this case citation.
So in this case, you don't have WIJ. So in the spectral CNN, W's come here. So these are the spectral representation of the filter. They are now replaced. Basically, you don't have arbitrary spectral filters. You have filters that look like polynomials, and the coefficients of polynomials are the parameters that you learn. Okay.
So is there, go to the result, so is there a way in some sense to tell in what areas of the graph you're getting the performance gain? Which I think would be equivalent to thinking about where are you leveraging stronger W's, right?
Excellent question. I don't know. We didn't look into it, so it's hard for me to tell.
So the reason, I mean, just motivated by this particular application, and maybe that's a more generally interesting thing for you guys to do. You know, there are some papers, you know, people in this room write papers. I mean, we're political scientists, right? But in this, we're not really political scientists, right? And so we're citing things that are well outside our field.
Yep.
And so that's going to be a very, like, the ability to then classify Gary King as a political science is going to actually be a really challenging thing to do. But the ability to, you know, someone who just writes about the Congress and whatnot, that'll be a lot easier to do. So it would be interesting to think about where your performance gains are coming from. Like, is it because you're getting Gary right, or is it that you're getting, you know, someone else right?
It's an excellent question. I don't know. Actually, well, it's not difficult to look into this interpretation of these results. Yeah, I think we can try to do it.
Do you have a comparison of time and space complexity of the spectral graph versus these other?
You mean the
methods?
other methods?
Yeah.
So, well, the other methods. So here, the complexity. It depends when you talk about complexity, whether it's complexity of the training or complexity of the inference when you apply the trained model. So all these methods have at least order of n complexity, which is also the complexity of the spectral CNN model. So I would say it's roughly the same complexity, at least as order of complexity. Then when it comes to constants, it might be a different thing, but as an order, I think it should be at least order of n. Okay, how much time do I have?
Half an hour,
Half an hour. Okay, good. I thought that only 5 minutes.
including questions.
Okay, good. Okay, so are we good with so far? Is it very different from what you usually hear?
It's much better.
Oh, thank you. Well, I was not necessarily expecting this kind of.
You'll soon be in our citation network.
Okay, good. So let's move on. So basically here, basically when these kind of filters are bad. Okay, let's look at. So this is a synthetic example. So this is a graph with strong communities. By communities, I mean that there are basically some clusters of vertices that are strongly connected between each other and loosely connected between across these clusters. Okay, and here the different clusters are denoted by different colors. So imagine that basically this is a group of people publishing together. Okay, and this is a group at another university. Maybe there are some collaborations, and right, you understand the idea. Okay, so basically there are communities. So if we look at the eigenvalues at the spectrum of the Laplacian of this graph, this is what we'll see. So we'll see a first few eigenvalues that are very close to 0, and then there is a jump, and the eigenvalues somehow grow. Okay. So basically, what happens here, if these communities were completely disconnected, so basically if our graph consisted, in this case there are 15 communities, so if it consisted of 15 disconnected components, then in this case we'll have a constant eigenvalue with multiplicity 15. Okay, so we'll have 15 times eigenvalue 0. Okay, because there are some connections, but there are weak connections, we don't have really 15 times eigenvalue 0, but we have small eigenvalues. Okay, basically if you think of it, Laplacian also has to do with diffusion. So if you think of heat propagation on this graph, it is very hard for heat to flow from one cluster to another cluster, but it's very easy to flow within the cluster. Okay. So basically, all the information essentially about the community structure is contained here at this low part of the spectrum, right? Do we have an agreement on this? So if you look at the spectral filters that we've seen before, the Chebyshev polynomials or polynomials in general, this is how they look like, right? So this is the spectrum of the graph. This is the low frequency that contain essential information about the communities. These are higher frequencies that are basically do not contain any interesting information. And this is how the filters look like. You see that it's very difficult with these filters to tell apart, for example, this frequency from this frequency, right? They are very smooth. So if I were really to localize in a specific frequency band, I will need to make polynomials of very high order, which are very unstable. Okay, so basically it will fail miserably on this kind of data set. And these data sets are very practical because we encounter community all the time in many realistic graphs. Okay, so the way to deal with this kind of problem is to, one way at least, is to apply a nonlinear transformation to our spectrum, or basically to our Laplacian. Basically what we want to do, essentially we want to zoom in on this frequency band, maybe to expand it, sacrificing some higher frequencies where we don't have important information. Okay, so the way to do it will be, one way to do it will be what is called the Cayley transform. So basically it's a complex function. It's a map from the real line to the complex unit circle. Or in our case, because the eigenvalues are non-negative, basically it's a bijection from the positive or non-negative numbers to half lower part of the unit circle. Okay, if you're interested in complex analysis, it's a particular setting of a Möbius transformation. Okay, doesn't matter. This is what it does. Basically, if we also allow to scale our frequency with some parameter h, we call it the spectral zoom. Basically, what it does, it can magnify our frequency. So these will be the frequencies that are mapped to the complex half unit circle. Basically, with appropriate value of h, we can zoom onto these low frequency band, and now we can clearly separate these values. So basically, we take the Cayley transform and we compute polynomials with respect to this Cayley transform. We end up with actually trigonometric polynomials. I don't want to go into the details, but basically these are well-behaved classes of functions. Okay. So again, if we consider these Cayley polynomials, so the coefficients, in this case, they can be complex coefficients, not real coefficients. We still have a constant number of such parameters. The filters do not have any more compact support, but they decay exponentially fast in some sense that we can define. It doesn't matter. Now, explicit computation, if you look at this thing, basically here it's applied to a matrix. It requires inversion of the matrices, Laplacian matrices, which if you do it explicitly costs n cube operations, which is of course a bad thing, but we don't actually need to invert these matrices explicitly. We can compute approximate inversion using, for example, Jacobi iterations, a few iterations of Jacobi, which again has linear complexity. So we are back to the good properties of linear complexity of this computation. So the spectral zoom allows us to give better localization and frequency, and also it's a richer class of functions compared to polynomials. So they are more suitable for modeling filters. And this is an example. So, well, this is a Euclidean example on a two-dimensional grid. This is how Chebyshev filters of order 3 look like. So remember, they have compact support, and that's exactly what we see here. Basically, they expand to 3 pixels beyond the central pixel, right? And this is how they look in frequency. This is Chebyshev of order 7, so they have bigger supports. This is Cayley of order 3. So because we don't have this restriction of support to be 3 pixels, they can be both localized and delocalized filters. So they can be also large filters, right? You see that this filter, for example, is large and this filter is very small. Okay, so back to this example, this is how the polynomial filters look like. Basically, we have the big trouble of distinguishing different frequencies. This is what we get with Cayley. So the spectral zoom allows us to magnify this band of frequencies where the important information about communities is contained, and we can localize filters at different frequencies. Okay, and this gives a huge difference in performance. So this is the performance of the Cayley filters, and this is the performance of the polynomial filters. Okay, and this is just a sanity check that the complexity of this approximate inversion has order of n, right? So it grows linearly with the number of vertices. Okay, maybe with bigger constant compared to polynomials, but at least the order of complexity is the same. Okay, and this is another plot that is actually very interesting. You can see that with just one Jacobi iteration in this approximate inversion, you get better performance than with polynomial filters. So the inversion can be extremely inaccurate. It doesn't need to be accurate because it is used as an intermediate step in learning. Okay, I will skip the other results. Let's look at another problem. So this is a recommendation problem. I guess you're all familiar with it. If you watch movies on Netflix, right? Netflix will suggest you some movies based on what you liked in the past, right? I don't know if you ever worked. I guess you did, right? They even at some point 10 years ago they offered a prize of $1 million to people who would be able to improve their recommendation results. So the usual way this problem is approached is algebraically. Basically, you have a huge matrix. Let's say the number of users by the number of movies. So typically the number of users will be in the tens of millions for Netflix, and the number of movies will be probably hundreds of thousands. Okay, so it's a huge matrix. And it is sampled only very sparsely, because even if you watch continuously movies throughout your lifetime, maybe you will watch a few percent of their collection. And let's say that the users can give different scores to these movies, let's say on a scale from 1 to 5. Okay, so you have a few of these numbers and all the rest is unknown in the matrix. And basically you try to fill in the missing values to interpolate this matrix. So the typical way of approaching this this problem is to find some kind of low dimensional structure that fits the data. Okay, and usually the low dimensional structure is understood by the rank of the matrix. So the rank of the matrix is the number of, basically the dimension of column or row space of the matrix. Basically, how many linearly independent columns you can have in the matrix. Okay, so if it has linearly dependent columns, it means that somehow there are few degrees of freedom that explain the data. Okay. Unfortunately, the minimization of the rank is a combinatorial problem that is NP hard, so it's usually replaced by a convex proxy, what is called the nuclear norm. So nuclear norm is sum of singular values of the matrix. Okay. Basically, if you heard of compressed sensing, that's the equivalent of the L1 norm for matrices. Basically, you're looking for this kind of minimization. So that was fundamental contribution of Emmanuel Candes, was one of the founding fathers of compressed sensing. So that's an extension for matrices. Okay, and usually this hard constraint that you want that at the given samples your matrix coincides with the given information, you can relax it as a penalty. So you want to be close to the given input. Okay, so that's the usual type of matrix completion. Basically, it's an algebraic problem. Of course, basically it has a clear deficiency. For example, what happens if you shuffle randomly the rows and the columns? The rank will not change, right? If you have an entire column that is missing, for example, a user didn't watch any movie, I'm a fresh user, I don't know what I would like, right? You can fill it in infinitely many ways, right? So basically, it doesn't have any geometric structure. So one way of introducing a geometric structure, maybe a naive way, but it showed to be quite efficient, is basically to replace this algebraic low-dimensional structure with another low-dimensional structure. Assume that we know a social graph of users. So social graph could be basically something that we build from the data itself, or maybe from some additional, such as demographic information. For example, we say that users are related if they have similar age, for example, or if they live in the same country, and so on and so forth. Okay, once we have this graph, we can talk about smoothness. Okay, so basically we want friends, so to say, so users that were represented by vertices that are connected. We want the vectors of the values that they give to different movies to be similar. Okay, that's exactly the Dirichlet energy. So now we have vector valued functions that live on this graph. Okay, columns in the matrix. Okay, and we can write exactly the same Dirichlet norm here that will promote this smoothness. So here, smoothness is understood. Basically, you can think of it as a low-dimensional model, but in a different sense. If something is smooth, it means that it can be represented with small number of linear combination of small number of flotation eigenvectors, right? Basically, it's a low pass signal in signal processing terms. So basically, you don't need many Fourier coefficients to explain these signals. So it is low dimensional, but in a different way from the previous model. And of course, you can also construct the same graph for the movies. So you have column and row graph, or user item graph, and you can also impose smoothness on the other graph, basically row-wise smoothness. Okay, so basically you replace the nuclear norm with these two smoothness terms with 2D Dirichlet energies. Okay, so here the main disadvantage is that the number of variables is equal to the size of the matrix, right? And usually these matrices are very large, so it's pretty hardly manageable optimization. So a different approach is to assume that the matrix is factorized. So basically you write it as a product of column and row factor, where one of the dimensions is fixed and small, independent on the input size, denoted by S, right? So basically this matrix is thin and this matrix is low, right? So here the total number of variables is linear in the largest dimension of the matrix. Okay, and basically the rank here is bounded by construction, right? Because anyway you are looking for low rank matrix, then here basically you just put an upper bound on the rank. Okay, and you can show that basically the nuclear norm, the minimization of the nuclear norm can be replaced by the minimization of these standard Euclidean norms of the factors. Okay, so this model was also adapted to the use of Dirichlet energies. You just apply them to each of the factors and not to the entire matrix. Okay, so that was one of the best performing matrix completion in NIPS 2015. Okay, that basically took the previous idea, just rewrote it in a factorized way. Now, if we look at this idea, basically smoothness is you can think of it as some kind of low pass filter, right? It assumes that the signal varies slowly across the graph. Now, nobody said that that's the good model for how the signal behaves on the graph, right? So basically, can we do something better? Can we learn optimal filters instead of assuming that it's simply smooth? Okay, and basically here it brings us to the point how to extend what we've seen before to multiple graphs. Okay, so basically, if before the main ingredient of filtering on a graph was a convolution, here it's a kind of two-dimensional convolution, right? Because we have two graphs. Okay, so basically, let's remind what is two-dimensional convolution. If you want to do Fourier transform of an image, how do you do it? You do it usually by doing a column-wise Fourier transform and row-wise Fourier transform, right? So basically, if an image is a matrix X, you multiply it by the Fourier basis matrix from the left and by the Fourier matrix Fourier basis matrix from the right. So you get Fourier transform of the columns, and then you do Fourier transform of the rows of the result. Okay, so basically you can write it like this. So the same concept can be applied now to a matrix that we want to complete. Now, basically you can think of it as a matrix that lives on the product space. Basically, we have two graphs. We have the graph of users, and the graph of items, or the graph of movies. And the Fourier transform that is associated with each of these spaces will be the set of orthogonal eigenvectors of the respective Laplacians. Okay, I denote it by phi C and phi R. Okay, the sub-indices standing for rows and columns. Okay, so that's the two-dimensional Fourier transform of such a matrix on these two graphs. We can define a two-dimensional version of a convolution, right? Exactly the same thing. So that will be Fourier transforms, their point-wise product, and the inverse Fourier transform. Okay. And we can also define, same way as we've seen, as we had polynomial filters before. Now we have bivariate polynomials. Basically, they depend on two frequency parameters, the eigenvalues of the first graph and the second graph. Okay, and exactly the same thing. So we have here a constant number of parameters that parameterize this filter. These will be the optimization variables in our learning. Okay, so this is an example of how these filters look like. So here, the two axes will be the column and the row frequencies on these two graphs. Okay, so basically this kind of multi-graph convolutional neural network allows to extract spatial features from the data. And then based on these features, we want actually to produce a new score matrix. So the way you can think of it is you start with some initial values in your matrix, and there is a lot of zeros, and you want to diffuse them, right? But diffuse them in a certain way that accounts for the structure of the graph. So basically there is a filter that tells you basically how this diffusion will be guided, and the filter, you learn it, and you also you also do it in an incremental way. So basically, it's iterative process where you take these spatial features that are extracted by multi-graph convolutional neural network, you use them to compute the update of the score matrix, constraining it, for example, to be an incremental update, so you don't change significantly the scores, and you repeat it several times. Okay, so that's the process that we do, and you can do it both in the factorized and the full in the full setting. Okay, so let me show you how it works. So it's a synthetic data set. This is the initial matrix. So it has a lot of zeros. Basically, these are the given samples, and these are zeros. Okay, and we measure the error as root mean square error. Okay, so the scores here are between 1 and 5, and the error here is very large, right? If 5 is the maximum value, that's the average error is more or less like a coin toss, right? So here it's the non-factorized, here it's the factorized version. But let's focus on this one. So after 5 instances of this process, we get a significant decrease of the root mean square error. This is after 8 instances, so it's already, you see here some structures emerge, right? And this is after 10 instances, the error is practically 0. Okay, so basically we recovered the underlying signal. And if you compare it to some state-of-the-art methods, it performs significantly better, while the complexity, in particular the number of parameters that represent basically the degrees of freedom of the problem, is significantly smaller. Basically here it's even constant, right? It's independent on the size of the matrix. So for example, overfitting will not happen usually. Okay, some other data sets that are popular in the matrix completion community, and it works currently better than any other method. Okay, at least on these type of data and these benchmarks. I guess I'm running out of time, so very quickly, we also talked about pooling, right? So basically pooling was reducing the size of the image in case of computer vision applications. Here basically on graphs, pooling can be done by graph coarsening. For example, if you collapse every time a pair of vertices into a single vertex. Okay, and computationally, if you reorder vertices in such a way that basically it corresponds to a binary tree, then you can just take you know basically which vertices will collapse, right? And you can take their maximum, for example, right? So same way as it is done in images. So let's do a sanity check. So this is a classical example that is used in computer vision to test image recognition algorithms. So this is an MNIST dataset of handwritten digits, images of digits from 0 to 9. And basically now we need to think of them as a problem of classification of functions on graphs. Okay, so you can think of a grid as a graph, right? In this case, it will be a regular graph. Each pixel is connected to its neighbors. Okay, and we have a function that basically the color of the pixel that lives on this graph. Okay, in this case, the grid is regular. What is important that the graph is fixed, but the data on the graph changes. Okay, a different way to think of it is to compute what is called superpixels. So basically, these will be blobs of approximately constant color. Okay, so basically, I will not go into details, but you can take an image and produce these superpixels in a certain way. And here, what is important that each image will produce different set of superpixels. So here, the graph and the data will be different. Okay, so remember in the beginning we mentioned that it's a big difference whether you assume that the graph is fixed or the graph is allowed to change. Okay, so let's see what happens. So now we are still in the fixed grid, and in this case we can also run the standard convolutional neural network, and you can see that let's say the spectral convolutional neural network performs roughly the same way as the Euclidean convolutional neural network, right? So at least this part of sanity check is working, right? Basically, we didn't by moving to the spectral domain and doing something that is more complicated than the simple correlation with patterns, we are not deteriorating the performance. Okay, what happens when we use the superpixels, basically the non-grid-like graphs? Of course, the standard convolutional neural network cannot be applied in this case, right? So we don't have anything, but you see that the performance deteriorated significantly, right? And that's because the spectral filter is graph specific. Basically, what the spectral convolutional neural network has a big trouble to generalize because the filter that it learns, it works on one graph, but it doesn't work on another graph. Okay, and here we have different graphs, so somehow the filters work badly on average. And the way to visualize it, so it's maybe hard to visualize it with graphs, so I will visualize it with discrete manifold. So you can also think of it as a graph, right? So you have points that are connected by edges, right? So we have basically, I just represented it as a surface. And so this is a surface of a horse. I have here some function, right? Basically these blobs of color. Okay, and I do a spectral filter that does a kind of edge detection. Okay, so it produces from this signal, produces this signal. Okay, and the filter is represented as a matrix W in the spectral domain, right? In the domain of the operation of the horse. Now, if I slightly deform this object, basically I change the graph, but only a little bit, right? Almost isometrically. Basically, the horse now will be moving. You see that the result is totally different. The basis here changes, right, with each different pose. The filter is kept the same, but the result is totally different, right? I don't get what I expected. And the reason is that the eigenfunctions, especially the high frequencies, the eigenvectors of the operation are extremely unstable. So this is the 50th eigenvector of the operation. You see how different it is in different poses, right? And this is a very mild modification of the graph. Here it is actually almost isometric. The weights, actually it's exactly the same vertices. The length, basically the weights between on the edges just slightly changed. Okay, and imagine what happens when the graph is totally different. Okay, so this brings us to in the remaining few minutes, to the spatial domain formulation of convolutional neural networks on graphs. And so we've seen the Euclidean version of convolution, right? So that was the spatial definition of convolution and the frequency domain definition of convolution. We've seen a straightforward way of generalizing convolution, basically by using the convolution theorem as a new definition of spectral convolution. The question is, what is the spatial equivalent of convolution? Is there a way to define it on the graph? And a way would be basically to consider some kind of local charting or local system of coordinates around each vertex. It doesn't need necessarily to be a bijection. So it doesn't need to be a unique system of coordinates from which we can necessarily recover the original representation. Basically, you can think of these as pseudo coordinates. It just allows to map the vertices with respect to the central vertex. Okay, I denote them by u, I prime. Okay, they might have certain dimensions. So it is actually much better defined on manifolds, because manifolds have low dimensional structure, local low dimensional structure that is called the tangent space. So two-dimensional surface, let's say a piece of paper, is locally two-dimensional, right? Even though I can bend it in any way. So that horse, for example, locally has a two-dimensional system of coordinates. On general graphs, it is much more loosely defined, but you can still think of some graph theoretical properties like geodesic distance, degree, etc., that basically will be defining around each vertex. Okay? And now we have a set of weighting functions. Let's say j such weighting functions that depend on these coordinates. So basically, here is an example of a weight, right? So here is large weight and black represent small weight. Okay, and we can define spatial convolution on a graph by taking the jth weight function with respect to my coordinates, right, around vertex I, applying it to the function at the vertex I prime. Okay, so basically this will be a kind of weighted average of the function on the graph around vertex I, right? This produces basically a j-dimensional local representation of the function around the vertex I, right? So it's a kind of a pitch, right? That's why we call it a pitch operator. And this will be the filter, right? So the local template that we'll be learning in the convolutional neural network. Now, in particular, we can consider these weighting functions to be Gaussians, where we actually we can learn the parameters of the Gaussians, the covariance and the mean vector. And if you rearrange these sums, you get basically what is written here as a Gaussian mixture. Okay, so that's why we call these mixture model networks. So basically, here are not only the weights of the template are learnable, but also the way that the pitch is extracted. the weighting functions themselves are also learnable. Okay. So again, if we go back to this example, this is how it compares to the spectral method. You see that we don't get almost any performance deterioration when we go to the unstructured representation of the images. And the core example of citation network, we get, well, insignificantly but slightly better results than the spectral convolutional neural network. So at least it passes the sanity check that doing something very different, we don't get worse results than what we've seen before. Okay, so in terms of applications, obviously computer graphics, well, here it actually made a big difference. Now, for example, problems like computing correspondence between three-dimensional shapes, these are the best performing methods. So you can find almost perfect correspondence between shapes in different poses, different kinds of noise and occlusions, missing parts, etc. Maybe more interesting applications are in high energy physics. So this is the LHC, Large Hadron Collider. Basically, it's a huge tunnel where accelerated particles almost to the speed of light are banked together, and basically when they collide, they produce thousands of other particles that look like this. So basically they get these kind of particle jets. So here is a collision event, and basically it creates a lot of other stuff that flies in different directions. So and along these curves they can measure, for example, the quantum momenta and different properties of these particles. Okay, so basically you can think of it as a graph, and you can classify the event. You can say that, for example, here the Higgs boson was created. So that was one of the things that they were looking for in the LHC. And another application. So if you thought that LHC is a big machine, so you can see humans here for scale, right? So that's a human, just to get an idea. So this is IceCube. So this is neutrino telescope in the South Pole. So that's only literally the tip of the iceberg. Everything is beneath the ice. So here the Eiffel Tower for scale. So it's really big. And basically these are sets of detectors. So again, they have basically it's a non-Euclidean grid. So it can also be represented as a graph structure. And when neutrino comes from space, in some cases it might interact with these detectors and create this kind of event. Basically, here the size of the ball represents the energy or some other properties of the interaction. And again, here the idea is to classify the events to say whether it was a neutrino or something else, maybe some background noise. And actually, I think in 1 year of observations, they observed 26 neutrinos. So it's a very rare event, but at least they observe something because these particles almost never interact. Okay, so last application I would like to mention is in brain imaging. So basically here it's actually an example of multigraph problem. So basically this is functional MRI. Basically you observe how the different regions in the brain react to different to certain stimulus. Okay, so the brain, well, we have different brains, but you can still align them to some kind of an atlas. So basically you can talk about regions in the brain and represent them as a graph or some spatial structure. We also have different patients that have some similarities. For example, their genetic background, maybe their medical history, their age, and so on and so forth. So we also have a graph of patients. And we also have a temporal domain. Basically, the temporal dimension is how the signal, the fMRI signal, evolves in time. Okay, so we have this three-dimensional matrix or a tensor. And we want, for example, to predict whether this patient suffers from Alzheimer's. Okay, so it's an example of a classification on multiple graphs. And there are many more applications. I didn't have time to mention all of these, so I hope it was interesting. And you can find more information, slides, papers, etc., code at this URL. So at this point, thank you very much.
All right, thank you everybody for coming, and I'm sure Michael would love to hear your thoughts if you want to email him maybe.